So if you do have questions and you're behind me, just like say, hey, Taylor, I have a question, because I don't have eyes in the back of my head, so I can't see you. But if you're in the front, hopefully I'll see your hand. So I'm going to be doing a bunch of random questions from this study guide. I tried to pick questions that were relevant to that little outline he sent you guys. Yeah. Okay, so the outline that he sent you guys, that's like a recommendation, I guess you would say. Like, he recommends that you cover those particular topics in detail. Of course, everything is fair game, but that's probably the most heavily tested material. Don't only study that though, because then that might not prepare you fully. Because, and those topics are super broad, so they can ask a bunch of questions from those topics. What I've been doing is, I would start with chapter 1 and flip through the book just really quickly, and if you see something you don't recognize, stop there and go over it. Try to maybe go over like Chem 1A today, Chem 1B tomorrow, and then both on Thursday, because then you've like at least seen everything. Yeah.
Like how big do you think terms are going to come into test? Like,
I have no idea. The only thing I'm going to say is because you have such limited time, they can't make the math very complex. So that probably means that a lot of the math you can use your conceptual like reasoning to figure it out. So I would say it's going to be pretty heavily concept based, but it might incorporate math with the concepts. I wish I could tell you more. I've never seen this test. I've never taken this test. I know the time limit stinks for you guys, but if they set it to that, that means they do expect you can finish it. So that's meaning the questions are probably fairly like basic in what they ask. Again, he does not make this exam, so that could be beneficial for you. Yeah. Yeah. Here. He's going to make a suggestion.
I don't know how loud to talk. Okay. There's like little self-assessment quizzes at the end of every chapter, and they have like the answers and stuff too. I've done chapter 1, 2, and 3 yesterday, so if you guys just go through those, they like pretty much hit like every single type of problem from the clinic.
Practice. No one? Okay. Let's go over some discuss in the first couple chapters. So I am not. So remember when we talk about this, they're two element, okay? This is an element. When we look at this fuel and an element, so these are two different charge. So phosphite is a -3. So you can view your chart, okay? I do recommend going over the ones that I would be familiar with the ones that I like always soluble, and then also I would like Thursday. At this point you kind of have to prioritize. So yeah. Any more questions? All right. So this right here, we're determining the concentration when we dilute a sample. So when you see the word dilution, you want to think of you're just adding more water to a sample and lowering the concentration. So if you're doing a dilution, you'll notice that you start and end with the same product. So the only substance involved in this is KCl, okay? All we're doing is adding more water to it. So there's an equation you can use, and it's M1V1 is equal to M2V2. The reason you can use this equation is because you have the same substance from the starting to the ending. If you start and finish with two different substances, you cannot use this, okay? So we need to figure out the molarity. So what we do, we assign M1, which is 0.188 molarity, times 25 milliliters, is equal to M2, and then we're going to divide by V2, which is 75 milliliters. You don't need to convert these volumes into liters because, as you can see, as long as they're the same unit, they're going to cancel out, okay? So it doesn't matter what units you use, just make sure from start to finish they're the same. So when you do this, when you solve this out, you're going to get A as your answer, okay? Any questions on that? All right. All right. I flipped to the third page, number 6. So here we're trying to figure out the insoluble product when we react two things together. So this is where you kind of need to know how the naming works and also your solubility rules. So we need to say the reaction between potassium and carbonate. So we know potassium is a +1 and carbonate, CO3, is a 2-, okay? When we combine them together, we get K2CO3. And then it's reacting with lead nitrate. So we have plus Pb. We don't know exactly what lead is, but we know nitrate is -1, so that's indicating lead is going to be +1. So we have this. Okay? Now, when you need to figure out what your two products are, the way I always learned it was you switch your dancing partners. I know it's kind of silly, but you're going to take the cation of one, and it's going to dance with the anion of the other. And then you're going to take the cation of one and dance with the anion of the other. Okay, so you just swap your dancing partners, and then your product is going to be PbCO3. The charge of lead is going to now change to a 2+ charge. And then we have KNO3 as your products. Okay? So when you look at your solubility rules, we know group 1 and nitrate are always soluble. So this product will be aqueous. However, if you look at your solubility rules, you'll notice that this compound would be insoluble. So that's going to be your solid product. Again, this is, as long as you know how to form your two products, it's just a matter of having memorized that solubility chart to figure out which one is solid and which one is aqueous. They could trick you on the exam, and if both of them are aqueous, please pick none of the above. So a lot of times they will trick you and not give you a solid product, and it's there to throw you off. So if you're 100% sure that they're both aqueous products, you just do not have a precipitation reaction. Yes? Can you show me that question later? So I would assume if none of the above is an option, even if it's slightly soluble, you'll still have, some of it will precipitate out, so technically you do form partially a solid product. It's just not a complete solid product. Good question. Any questions on this little thing right here? This is PbCO3. Did you look up lead by any chance? Can somebody Google, does lead always have a +1 charge, or is it a transition metal that varies? Somebody just let me know. It varies? Okay, so then yes, it would adjust to form, because carbonate is always -2, so the charge of lead would change to fix, like to accommodate that. Yeah, yes. I'm sorry? I didn't balance the equation. Yeah, so you would, the balancing isn't important for this particular question, but you do need to know how to balance equations. So make sure that you would do your coefficients accordingly, okay? Any more questions? All right. Flipping over one page. All right, so we need to identify the spectator ions in the following half reaction. So the first thing when you get a question like this, you need to figure out what the two products are that form. So we're going to swap our dancing partners again. So you'll get KNO3, and then, bless you, CaCl. Okay, was this the question? By any chance or no? Okay. Sorry, side note. When you do these two products, you will notice, remember, group 1 and nitrate are always soluble. When you look at your solubility rules, however, this is also a soluble compound. So both of them are aqueous. So if you do not form a precipitate, there's no way for you to have spectator ions. Because what spectator ions are is like if you have a precipitation reaction, the spectator ions are the same from beginning to end. But if you don't have a precipitation reaction, you would never assign anything as a spectator ion. So E is your answer because no precipitate is formed, so you don't really have spectator ions. Yes? No, because you would know that if it forms a solid product, then it would be a precipitation reaction. Hopefully they will to be nice, but they don't technically have to. Okay? So remember how you have 3 types of equations. You had the molecular equation, the complete ionic. Do you guys remember these? And the net ionic? These are, when you're writing out precipitation reactions, these are 3 different equations that you would need to know how to write. So the molecular is what you see right here. Everything nicely written out, balanced, okay? So this is the balanced equation. The complete ionic, it just means that you separate all of your compounds into its anions and cations. Like you would literally just write it as like K plus, Cl minus, plus Ca2 plus, and so on. When you write your complete ionic, your solid product does not separate. Do you guys remember that? Yes, no, maybe so? Okay, so the complete ionic, when you break apart all of these into their ions, if you have a solid product present, that would stay together. And then the net ionic, you remove your spectator ions. And the spectator ions are the ones that look the same from beginning to end. So they are not involved in forming the precipitate. Okay? There's a really good explanation in your textbook. I know I just briefly discussed it, but they'll show you step by step. So do make sure that you go over that in your textbook. Okay? Yes? So they could still give you this type of equation, and you would form the products, and then you would say which one's insoluble, and then you would have to go through and do the whole thing. I don't think that they're going to make you do all of that because that would take a really long time. So what they might do is just show you the products, and then your spectator ions are always going to be the ions that form the aqueous product. Okay? Any more questions? Okay. Another way to think of it is spectator ions are always soluble. Okay? So they're never going to form an insoluble product. Okay. So I'm flipping over one page. And doing the one that says an ibuprofen suspension. So this is kind of a conversion factor, weird stoichiometry problem that you guys are going to need to know how to do. So we're trying to figure out how many milliliters. So our answer needs to be in milliliters. And then we're given a bunch of random conversion factors. But we start with 35 pounds. Okay? When I do these problems, I find it easiest to work backwards because then you can like figure out the stepwise to get your right answer, but you guys can do it however you want. So what I always do is I say I need it in milliliters. What's present here that could give me milliliters? Well, we have a conversion factor right here that's milligrams per milliliter. So we can work backwards. Our milligrams per milliliters. What would have gotten rid of milligrams? Okay, we have a milligrams per kilograms conversion factor. So we're still working backwards. Okay, what would get rid of milligrams? Or I'm sorry, kilograms. Well, we have this conversion factor right here comparing pounds to kilograms. So we would say pounds per kilograms. Again, this, and then that would give you pounds. This is the backwards stepwise function. So then all you need to do is start here and then flip them to get you your right answer. Because we started with pounds and ended with milliliters, so we worked backwards. So then what we can do is begin. 35 pounds. Okay, then we know we have a pound per kilogram relationship. We need kilograms on top so that we can get rid of pounds. Yeah, any weird conversions they're going to give you, yeah. But your like 10 to the whatever, they wouldn't give you those. So like deci, centi, milli, kilo, make sure you know at least those conversions. Okay, so we got rid of pounds. Now how are we going to get rid of kilograms? Well, we have this conversion factor right here. So we have 10 milligrams per 1 kilogram. That gets rid of kilograms. How are we going to get rid of milligrams? Yep, 5 over 100. And now we're in milliliters. So if we cancel out our units, our answer will be in milliliters. And when you solve that out, you're going to get 7.9 milliliters. I know that these questions can be a little bit like confusing and scary, but the way I do it is just always try to set your conversion factor up to where the units you need to get rid of cancel. So you always have top and bottom cancel. And then whatever you need on top. So you can kind of play around with these if you get completely lost and just try to cancel the units until you get into the units you need. And usually it will work out for you. Any questions on this? Okay. The next question, we start with grams and we need to go into atoms. So if we're going from grams to atoms, is there a conversion factor that takes you straight from grams and puts you into atoms? Yes or no? No. We need to go from grams to what first? Good. So you have to go to moles and then moles to atoms. You can never go straight from grams into atoms because you know Avogadro's number is atoms per mole. So grams to moles comes from the periodic table, and then moles to atoms is Avogadro's. Okay? So we have 5.4 grams of lithium times 1 mole over 7 grams, that's from the periodic table, times 6.022 times 10 to the 23 atoms per 1 mole. Avogadro's number is always this number of something per 1 mole. It's always per 1 mole. It could be atoms, molecules, particles, ions, ice cream, cookies, cake, Four Rivers, Coca-Colas, it doesn't matter. It's this many of something per 1 mole always, okay? So when you answer this out, you get 4.7 times 10 to the 23rd atoms. Yes? I would briefly go over sig fig rules, yes. It's not super important unless it's actually asking you in the question for sig figs. But just briefly go over them to be safe. Yeah, I don't think that it's going to be of too much importance. Sorry, I'm pretty lazy with my sig figs, so I probably won't be doing those rules, but just keep that in mind. Any questions on this type of conversion? Okay. So, this is talking about an isotope. What are isotopes? Of your 3 subatomic particles, which one differs? Neutrons. So in isotopes, your neutrons are what differ, okay? Just a quick quiz question. What makes up the nucleus? Newtons. Fig Newtons? No. Neutrons and protons make up the nucleus, and then the electrons float around. Which of those 3 particles defines the element you're looking at? Protons. And which 2 will be the same in a neutral element? Protons and electrons. So when you have a neutral element, the protons and electrons are the same. Good. So isotopes, again, differ in neutrons. What's the charge of a neutron? 0. It's neutral. Good. Okay. So when we need to calculate using our isotopic abundance, the general equation you're going to use is mass of isotope A times percent of A plus mass of B percent of B, and so on, dot, 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 because you can have a million isotopes, it doesn't really matter, is equal to the atomic mass. The atomic mass is what you get from the periodic table, okay? So when you read these questions, sometimes you're solving for this, but sometimes you'll need to solve for one of the masses of the actual isotope. If you're solving for one of these masses, it might look like in the question you have 2 unknowns, but remember, you just grab this number from the periodic table, okay? So don't let that confuse you. In this particular question, we're trying to do, this is what we're doing actually, determining the atomic mass of the second isotope. So let's try to figure out how we go about doing this. So the mass of the first one is going to be your 80.9163. And then you have it times your percentage. It gives you your natural abundance. Do you multiply it by 49? What do you have to do? Yeah, so please make sure you put it in its decimal form, otherwise you're going to be off. So 0.4931. And then we have plus mass of B, so that's our unknown. How do we know what the percentage of B is? Yeah, so it looks like you have that as an unknown, but you know this is going to add up to 100%, so you just do 100 minus that percent. So you're going to get 0.569. Now, again, it doesn't give you the atomic mass, but we do know that it's bromine. So we look at the periodic table, and we're going to set it equal to 79.9. Okay? When you multiply this out, you should get 78.92 as your mass of the second isotope. Bless you. So again, you could be solving for one of these masses of the individual isotope or the atomic mass. But this is the equation no matter what if you're doing an isotopic abundance question. Just to have, because a lot of the stuff that he sent you, so I'm not going to focus on that as much unless we have time. Okay? So I'm going to do this question right here. I literally just flipped to the back, so we're still on the same paper. Okay, so we have 0.152 moles, blah, blah, blah. Which sample has the smallest mass? When you get a question like this, please don't go through and solve out each one of these. Think about it conceptually. If we have moles and we need to go into grams, we are going to do number of moles times number of grams per mole. That's your typical conversion, okay? So if we want the smallest number of grams, what do we want the molar mass to be? As small as we can get it, okay? Because if you multiply, they all have the same starting number of moles. If you multiply this by a small molar mass, your answer is small. But if you multiply it by a big molar mass, your answer is huge. So to get the smallest mass, you pick the one with the smallest molar mass. Okay? So you do not need to go through and solve all of these out. Does that make sense to you guys? So when you guys were asking me like if it's going to be concepts or math, this is kind of a question where it kind of is math, but not really. So that's probably how they're going to ask them, because none of you guys because you're here, but everybody else that didn't show up will sit there and solve each one of them out and waste 10 minutes. So, but you guys are rock stars now, and now you know how to do it without solving math. Does anyone have questions on this? All right. So we're going to move down to the question below. We're trying to find the mass in grams of the calcium ion present in some mass of this compound. Okay, so this is where you need to use your mole to mole ratio. You can use the mole to mole ratio when you're going between two different compounds, or when you're comparing one thing within one compound. Somebody eating something? Smells like, I just got a whiff of something that smelled good. When I walked in, it smelled like syrup, and I was like, pancakes. Okay, sorry, side note. I had pancakes for breakfast, actually, and they were good. Okay, so if we're going to do this, we need to eventually get to our mole to mole ratio. Our mole to mole ratio of calcium to calcium phosphate is, for every 3 moles of calcium, you guys can't really see that, can you? For every 3 moles of calcium, we get 1 mole of calcium phosphate. So the first thing we need to do is change our original mass in grams of calcium phosphate into moles. And they're nice and give you the molar mass. That was nice of them. Okay, this is moles of calcium phosphate. Okay? Now we can do our mole to mole ratio. So for every 3 moles of calcium, because there's 3 calcium ions in calcium phosphate, we have 1 mole of calcium phosphate. Okay? Now it's asking for the mass in grams of calcium. So the next step you have to do is just multiply it by the molar mass to convert it into grams. So this is going to give you 2.405 grams of calcium. Does that make sense? B. Any questions on that process? Okay. Then we move to the one below. Oh, I'm sorry. Yep. All right. So the next question, it's saying in a particular titration reaction, and then we have a bunch of other crap happening. Okay. So when you see the word titration, this is solution stoichiometry. If you notice, we start with copper 2 chloride and we end with sodium phosphate. So we're converting from one reactant to the next, so eventually we're going to have to get to the mole to mole ratio. I want you guys to get in that habit of always thinking mole to mole ratio. So the next thing we need to do is figure out how are we going to get there. So we see things in terms of milliliters and things in terms of molarity. What are the units of molarity? Moles over liters. So if we need to solve for moles, we need to multiply the molarity times the volume. So that's what we're going to start with. So we're going from copper 2 chloride into sodium phosphate. So we're going to start with, we need to convert our milliliters into liters. So we have 0.0954 liters times 0.204 moles per liters of copper 2 chloride. That leaves us in units of moles of copper 2 chloride. Once we're in moles of copper 2 chloride, we can use our mole to mole ratio. So we have for every 2 moles of sodium phosphate, we're going to get 3 moles of copper 2 chloride. So now we're in moles of sodium phosphate. But you're trying to figure out what the volume of sodium phosphate is. So we need to use the molarity that's given. We know molarity is moles per liter. So we're going to say for every 1 liter, we have 0.35 moles. This molarity can just be used as a regular conversion factor. Just realize that the number is always attached to moles, and it's per 1 liter. So our units are going to all properly cancel, and you're going to get 37.1 milliliters. Sorry, then you convert it into milliliters. Okay? This is a pretty complex solution stoichiometry, or this is a pretty complex stoichiometry problem. Please do know how to do it, because this essentially could be done fairly quickly, so I think this is definitely fair game. Because it does incorporate molarity and stoichiometry at the same time, so it's kind of killing 2 birds with 1 stone. So please make sure you know how to do this. And it was on your little study sheet, so I would assume it's probably on the exam. Any questions? All right. Flipping the page to limiting reactants and theoretical yield. This is everybody's favorite topic in Chem 1A. Was it your guys's? So did you guys like limiting reactants or calorimetry better? So who was better at limiting reactants? Who was better at calorimetry? Who said screw both of those? All right, well, we'll make sure you relearn them. Yeah, they're a lot of fun, but luckily he only put coffee cup calorimeter, so I don't think you need to know the bomb. Okay? So this first question is asking you to calculate the percentage by mass of hydrogen. Okay, so let me zoom in so you can see the compound. It's C4H8O. We're trying to figure out just hydrogen. So the percentage of mass is going to be the mass of hydrogen over the mass of the compound. Sorry? Exactly, yes. So it's the mass of hydrogen times how many there are in the compound. So here you say 8, and then the mass of the compound is 72. 8 because there's 8 hydrogen times 1 from the periodic table, and 72 is the molar mass of this whole thing, times 100, which is going to give you 11%. Okay? So they could have asked you carbon, and there you would have just put what? What would be on top? 48 over 72, and then oxygen would be 16 over 72. And all of those would add up to 100%. Okay. All right, so flipping the page, we have to do some empirical formula work before we move to limiting reactants. Empirical formula was also kind of a doozy in Chem 1A also, but we'll make sure you get there. So I just flipped the page by 1. This is the second question on the page. So when they give you, okay, we're trying to figure out the empirical formula. Bless you. Remember that the empirical formula is the condensed version of the compound. Molecular formula is the real compound. When they give you percentages, as you can see, this adds up to 100. So you need to just assume 100 grams. So you would literally just X out the percentages and change it to grams. Okay? Don't confuse yourself. Now, when you're doing empirical formula, step 1, you're going to convert the grams into moles of each compound. Step 2, you're going to divide by the smallest mole value of the 3 in this example. That's going to give you your pseudo formula. If the factors are not whole numbers, make them whole numbers. Okay, so that's the step-by-step process. So let's see how this is done. So we're going to say 21.7 grams of carbon. We're going to convert it to moles. Bless you. Bless you to everybody that sneezes from now on. Are you guys excited that today is the last day of a lot of your guys' freshman year? You guys are sophomores now, if you're a freshman now. That's exciting. Now the real stuff comes, right? Now you have to get down to business. All right, so we converted all of our starting grams into moles. The next thing you need to do is divide all 3 of them by the smallest molar value. Because what this does is it gives one of them in a ratio of 1, so you have a 1 to something factor. That lets you compare the ratio of the atoms involved. So we get 1, we get 6, and we get 3. So for our empirical formula will be C3F6O. This is our empirical formula. If they were to give you the mass of the molecular formula, you could use that relationship to figure out what the molecular formula was. So let me show you an example. I'm just going to do a side note example. Okay? So if your empirical formula is CH4, so say we calculate that out, and then I say the molar mass is 32 grams per mole. And then I want you to calculate the molecular formula. Okay. So again, the empirical formula is some ratio of the real thing. So if the molar mass is 32, we need to figure out the molar mass of the empirical formula. So the molar mass of the empirical formula is 16 grams per mole. Then we say how many times does the empirical formula go into the molecular formula? It goes in 2 times. So we say the empirical formula times 2 is the molecular formula, which is equal to C2H8. Does that make sense? Okay. Any questions? Good. So now we have reached limiting reactants. What chapter is limiting reactants? 4? I think it's 4. Okay, so this question is asking for the percentage yield. The formula for percent yield is actual over theoretical times 100. If you forget this equation on the exam, please don't worry. If you get more than 100%, you did the equation wrong. So if you get over 100% yield, flip the ratio or flip the fraction, and then you'll get the right answer. Unless you did the whole math problem wrong, which none of you guys will, but that's okay. All right, so the first thing we need to realize is the limiting reactant is going to be what determines your theoretical yield. Because as soon as you run out of your limiting reactant, you cannot react anymore. So when you're doing these problems, they're going to give you grams of your 2 starting products. So they give you 31 grams of benzene, which is this guy right here, and 65 grams of bromine, which is right here. And then it says 41 grams of bromobenzene are obtained. What does this value indicate? It's actual yield. So we know actual yield is 41 grams. That has to be given for you to determine the percentage yield. Okay? So the first thing you need to do when determining limiting reactant is you need to convert both of your grams into moles of starting reactants and then convert them to the product that you're looking for. So we're going to start with 65 grams of Br2 times 1 mole over 160 grams of Br2. This is very important. This is diatomic, so please multiply the mass by 2. So don't accidentally put 80 as your mass, okay? And then we're going to convert it into our bromobenzene because this is the guy we're looking for. So for every 1 mole of bromobenzene, we get 1 mole of Br2. And that yields this many moles. We're going to do the same thing for our benzene. We have a 1 mole to 1 mole ratio, and that's going to give you 0.397 moles. Once we're here, can you determine the limiting reactant? Yes. How do you know which one's which? The smaller the number of moles indicates your limiting reactant. Please don't look at your grams in the beginning and pick the smaller one and say one of them's the limiting reactant. This is the most common mistake. They'll be like, oh, 31 smaller, so it has to be limiting. No, you need to compare how many moles of product are actually produced. Because what this says is when all of this reacts, you produce this much product. Okay? So from this point, all right, we know the limiting reactant, but we're still trying to figure out percent yield, so we need to figure out the theoretical yield in terms of grams. So now we just need to multiply by its molar mass to convert it into grams. So that's our theoretical yield. For our percent yield, we're going to take 41 over 62.329 times 100, and that will give you 66%. Again, this is very complex, so I don't think you're going to have to do something this extensive. You'll probably have to do one component, so you'd be like, you'd have to either solve for the limiting reactant, or they would give you the limiting reactant and then you just need to solve for the percentage yield. But if you know how to do the entire process, you should be able to do any subdivision of it. Okay? Any questions? Alrighty. So let's flip the page. How do you guys feel? Are you feeling better? Do you guys feel like you remembered a lot of this or no? Are any of you more nervous than when you came in? Yeah. Please don't be. Okay? We'll get you guys there. Does anyone have any questions up until this point? Page 9. So the page we were on, it's the next page after that. The first question, oh, let me zoom out. The first question is in the, wow. That's the first question on the page. I'm doing the second question though.
We're doing the same thing you do. Yeah.
What?
We only have the packet. Yeah, we have like each chapter.
No, oh, no, there's a link to another website on my thing that has this whole packet. Yeah, it's called the ACS Study Guide like the ACS final study guide. This whole packet is online. Yeah. Sorry, I didn't mean to make you guys like flip through all that crap. Yeah, this whole study guide is actually online. It's just on a different link than where all the other practice tests are. So, okay, you know when you go to my regular Google site, in the hey guys, if you can listen really quick, in the comments section, there's a link that I posted. Click the link, and there's like literally everybody from SI is on that. Scroll down until you see Taylor K with Chem 1B, and there's a million files in it, because I posted all the answer keys. But it's called ACS Study Guide. Will it show up on the DocCam? I mean, at this point, you can't print it out anymore because you're already in here. So for when you are done here, you can go access that from the website. Okay? Thank you, though. All right, so sorry if you didn't find that at first. I didn't mean to make your life more miserable than it is. I tried to make it easy for you. Also, all of those practice exams that I posted for you guys, remember, you can't assume that's what the exam is really going to be like. I just wanted to give you guys as many practice questions as I could. And don't freak out because there's so many. Like, you don't have to take them if you know how to do that material. I was just trying to give you guys as much as I could. Okay, so this is another limiting reactant question. So it's saying how many moles of nitrogen monoxide we can make from these two starting reactants. So as we can see, this question doesn't tell you it's limiting reactant, so you need to be very careful with how it's worded so you can realize it is a limiting reactant question. So again, it gives you two starting reactants, and you need to figure out how many moles of that product are produced. So please notice it already gives it to you in moles. So it's trying to make your life easier. Before it was given in grams and you needed to convert to moles, but here it's a step quicker. So we have moles of NH3. We're going to use our mole to mole ratio. So for every 4 moles of NO, we have 4 moles of NH3. And that's going to give you 1.9 moles of NO. Then we have 3.5 moles O2. Our mole to mole ratio is for every 4 moles of NO, which comes from the balanced chemical equation. We have 5 moles of O2. This gives us 2.8 moles NO. So we're at the point now where we can determine what the limiting reactant is. Again, it's the smaller one. So this guy right here is going to be our limiting reactant. It's asking for how many moles of product are made. So this limiting reactant is the theoretical yield. And since it needs it in moles, you don't need to convert it to grams. So your answer will be A. So this is I feel like this is probably how they're going to ask the question because it's a very quick limiting reactant question. But again, if you knew how to do the one we did previously, you'll know how to do this one as well. Yes?
So, in the ACS review book for some of the practice questions that they provide if you have a really large compound, they provide
The molar mass?
molar mass of it. Do you know if that's how it's going to be on the exam?
Usually, if they're really complex, they'll provide them. But if they're just like 2 things, then you'll have to do it yourself. But usually, if it's like a ginormous compound, they will give it to you. Yeah. Always double check. Usually they will be balanced, but I can't guarantee. Usually the only time you have to balance it is if it's a balancing question, but I don't know how tricky they're going to be on the exam. Maybe. I don't know how it's going to be presented. But if you see an equation that has no coefficients, that should be a sign for you just to check. It might be balanced, but if you don't see coefficients, there's a chance that it wasn't balanced for you. Any more questions? Okay. All right, let's do number 7. Okay. So we're trying to figure out how many moles of excess reactant are left. So this is another limiting reactant question. It's just one more step is added to it. So it's kind of like the worst of the worst. So I'll make sure you know how to do it, and if you get it on the test, you'll be great. So the first step is you need to figure out what the limiting reactant is. So you're going to follow the exact same process. So here, because you're trying to find the excess reactant, it doesn't matter which product you convert them to. Just make sure that you do convert them to the same product. So I'm just going to convert them both to water because it's easier for me to write. And I'm lazy. Have any of you ever been so comfy in your bed and your light's on and you're like, I don't want to get up to turn the light off, so you just sleep with the lights on? Yeah, that's my level of laziness, like all the time. Actually, where I used to live, the guy in the apartment guy that was selling to me, he goes, I ride the golf cart everywhere around because I refuse to walk. He's like, I'm so lazy. And I was like, oh, okay, I guess. He was a crazy driver too. All right, so I converted them both into moles of the same product. So this is our regular limiting reactant type question. So as we see, our NaOH is going to be the limiting reactant because it produces less product. So that means CO2 is the one in excess. But we need to figure out how much of our original amount is left over. So what we do is we're going to convert, so this is the process for excess. Convert limiting reactant into excess reactant in terms of moles, because that will tell you how much of the excess reactant was used. So we take 1.85 moles of NaOH, and we use our mole to mole ratio between limiting and excess. So we have 1 mole of CO2 to 2 moles of NaOH. That gives us 0.925 moles of CO2. This value right here is how much was used, not the excess. So we need to take our starting amount, which is 1 mole, minus what was used up. So this is how much is in excess. I know this is complex, and I'm sorry, but it's Chem 1A. I'm also aware that there's many different ways that you can solve these problems out. If you have a way that works for you and has gotten you the right answer every time, you don't have to follow the math that I use, okay? This is just over the years the way I've found is easiest for people who forgot it to understand. So again, if you know a different way, by all means you can use that. Any questions on this? Yes? Because, oh, okay. So in this question, I'm going up to the one we just did before. This right here was the limiting reactant. So when you completely use up this reactant, that determines exactly how much product was yielded. So how much product is produced is your theoretical yield. Does that make sense? Okay, great question. Any more questions on this? Okay. So I'm flipping the page to the one labeled combustion analysis. This is definitely a favorite. Okay. We got this, we'll be fine. All right. So, with combustion analysis, you always have a hydrocarbon, which is a C and an H compound, reacting with oxygen to form CO2 and water. So backtrack to the question that we were doing empirical formula. This is pretty much the same type of question, just with an extra step added to the beginning. So remember, for empirical formula, we needed to figure out the number of moles, and then you divide it by the smallest number of moles. You're still going to do that here. But let's see what comes first. You have CO2 and water. You need to isolate carbon and hydrogen from these two compounds. In order to do that, you need to compare the mole-to-mole ratio, like we did before. So combustion analysis kind of combines combustion analysis, or empirical formula, and stoichiometry. So we're going to do that first. We have 33 grams of CO2. The first thing is we need to do the get to the mole-to-mole ratio. So first we have to convert it into moles of CO2. Now, for every 1 mole of carbon, we have 1 mole of CO2. Okay? And that gives us 0.75 moles of carbon. We're going to do the same thing for the hydrogen in the water. For every 2 moles of hydrogen, we have 1 mole of water. Does everybody understand how I got these 2 mole-to-mole ratios? Does anyone have issues? Okay. So we have 1.5 moles of hydrogen. At this point, this is where you do the stuff we did before. So we're at the point to determine the empirical formula from before. In this particular good question. So he asked if you need to find the oxygen. There's 2 types of combustion questions. This is the easy one because you only need carbon and hydrogen. If they give you the mass of the starting sample and they tell you that oxygen's in the compound, you need to do the harder one, which involves oxygen as well. But this particular question does not have that. I am going to do an example pretty soon that has all 3, so you'll see the difference in the question type. So once we're here, we can divide by the smallest number of moles to get our ratio. So we divide by 0.75 in both of them. That gives you 1 to 2. So your empirical formula of this combustion analysis question is CH2. Any questions? Good. Does that help, or are you guys still completely confused with combustion analysis? So the process is grams of CO2, H2O, to moles CO2, H2O, to moles C and H, to divide by smallest. That's the stepwise process every time. So if you're somebody who just likes to see the conceptual side of it, that's the steps you would take to solve a combustion problem. If that's confusing, ignore it. Okay? All right. So this is asking you to determine the molecular formula, and it gives you the molar mass of that molecular formula. So remember that side note question I did? This is the same thing. So you're going to need to first determine the empirical formula using these things right here. What time is it? You guys can do this one on your own. But you determine the empirical formula first, find the mass of it, and ratio it to this mass. I already did a problem like this before. It was the side note question, okay? All right, so I'm flipping the page. And now I'm going to do the even crappier combustion analysis where it has carbon, hydrogen, and oxygen. So the first thing is the compound contains carbon, hydrogen, and oxygen, so you know that your formula should have all three. And also it gives you the mass of the sample of that compound. So the original process is identical, so let's start it out the same way. You need to first isolate carbon and hydrogen, so let's do that. So this, again, is exactly the same as what we've did in the previous problem. Okay. So we have isolated the moles of carbon and the moles of hydrogen. However, we need to figure out what part oxygen contributes to this compound. So the whole sample weighs this much, and that contains carbon, hydrogen, and oxygen. So with this right here, we can figure out how many grams of carbon and how many grams of hydrogen are present in this sample. Sorry that I'm running out of space. Okay, so these two values are how many grams of carbon and hydrogen are in this compound. So if you add these up and subtract them from the starting sample, that will tell you what left over is oxygen. So we can say 0.8009 minus and that's the grams of oxygen in the sample. So we have how much each one contributes to the sample, but again, remember we're determining the empirical formula. And to do that, we need to find the ratio between the number of moles. So we need to convert our oxygen into moles. Okay. Now we have moles of carbon, hydrogen, and oxygen. At this point, it's identical to every other empirical question, where you divide by the smallest number of moles. So the smallest one here is the 0.018. And that gives you C2H4O. I know this is scary. Are you guys okay with it? Okay? Please keep practicing. Don't expect to get it in one shot. So if this is your first time reviewing it, of course you don't remember. So please just review in your textbook and keep going over that stuff, and eventually it would make sense. Does anybody have questions, though, in general on combustion analysis? Okay. Are you guys all going to ace this test? Yes. Thank you. Say it with pride. Yes, we are going to rock it. Is there a curve? I don't know. Okay? I hope so for you guys, but I don't determine that at the end. So just ace this exam and then you won't need a curve, right? You guys will ace it. Okay? Don't worry about the curve. You have to take the exam regardless. You're already in it. You can't withdraw anymore. So just do your best. Okay. I'll give you guys like 10 seconds to have your discussions and then we'll get back to it. So take a little brain break because I'm a little tired too. do some stretching, stand up, stretch your legs. What? Hey.
Hey, what's up?
Nothing. I'll see you in like an hour.
So much to ever done.
Yeah, you guys are going to be sick of me soon.
Huh?
You're going to be sick of me.
Whatever. Thank God. Lily's like, yeah, I did 4 hours in one shot. I'm like, oh my God.
That was a lot. Even I was like, all right, so we've had a few moments. Hopefully you guys are recharged. So let's get into thermochemistry. This is kind of another evil topic. Usually people associate math with being evil, so I'll just continue that idea. But hopefully it will make sense after we go over it. Okay, so we're going to do this guy right here. We are determining the specific heat capacity. We're given the mass, we're given some temperature change, and we're given some unit of energy. So this is where your equations are going to come into play. We're going to use our Q is equal to MCAT equation, where M is mass, C is specific heat capacity, and T is the final minus initial temperature, and Q is heat, okay? So if we're solving for C, we just need to manipulate this equation to get Q over M delta T. And then we just need to plug it in. They give you the units in your answer, so just make sure the units you use in the question correspond to this. So the only thing you need to change is the units of temperature. To go from Celsius to Kelvin, remember you add the 273. So you're going to get these values, 308 and 343. And then you do final minus initial, which will give you 35. So we have 136, which was given, times the 8.73 grams, times 35 Kelvin. Did he say that there were going to be a lot of questions that required you to know equations? Do you guys remember? He didn't say anything? Okay. Yeah. Yeah, because you need to because the units are Kelvin. But if they were Celsius, you wouldn't need to. Like SPDF?
No, like the sigma 2
Oh, the molecular orbital theory. Yeah, okay. Just to let you guys know, so she said she talked to Dr. Fraser. You guys remember molecular orbital theory where it was like anti-bonding and bonding, sigma 2s star. She said that's not on there. So don't waste your time. Okay? That's what he said.
Yeah.
But, okay, we'll just leave it at that. I'm not guaranteeing it because, yeah, I don't know anything. Yes? I'm sorry? Yeah. So, just to go over this again, Q is the heat. That will be in terms of joules. M is the mass in grams. C is the specific heat. This is a constant. And delta T is the temperature in terms of Kelvin. So you need to convert these to Kelvin, and then you would get your delta T, which is final minus initial. Okay? Yeah, if the units of the answers were in Celsius, you would not need to change it. Yeah, good question. All right, flipping the page. I'm going to do the last one on the sheet. Okay. Which would show the smallest temperature change upon absorbing 100 joules of heat? So again, you do not need to do the math of these. You just need to compare the relationships. So we have our Q is equal to MCAT again. We want the smallest delta T. So if we have delta T is equal to Q over MC. Our masses are all the same for all of them, so we don't need to look at that. Our joules are the same for all of them because they're all absorbing 100 joules, so we don't need to look at Q. We are only looking at the specific heat, which is different for each substance. So if we want T to be very small, what do we want C to be? Really big. So decreased delta T is an increased C. So you just pick the one with the largest specific heat capacity, which is B. Again, you do not need to solve each one of those out because you only have like a minute per question. Yes? Sorry, what did you say? In this question, it wouldn't affect it, but your value would just be negative instead of positive. But it wouldn't adjust how you do the equation.
But wouldn't you want it smaller negative numbers?
Water holds a lot of heat, so if it puts out a certain amount, that would change.
But it doesn't matter which way you're moving the temperature or which way you're moving the heat, because if you're asking for the one that would have the smallest temperature change upon releasing, it's still going to be the same answer. It's just the energy is going in a different direction. Does that make sense? Good? Okay. That is important, though, in other types of questions. Okay. Flipping the page a couple times. So I flipped it once. Then I'm going to flip it again. And then you see the page labeled coffee cup calorimeter. Bless you. I'm going to do the second one on the page. Okay. There's a lot of stuff happening here. We have volume and molarity. We have volume and molarity. We have a temperature change. We're calculating delta H of the reaction. They give you density and specific heat. So let's kind of break down how to do this problem. The first thing I want you guys to realize is delta H of reaction is equal to Q of reaction over moles of our substance. Here it's AgNO3. Okay? Also know that Q of reaction is equal to negative Q of solution, and Q of solution is equal to MC delta T. All three of these are equations you need to know to solve this problem. Okay? Because remember, if your reaction releases some amount of heat, the solution will absorb that much also. So they're like inversely proportional. When you do the MCAT equation, it's specifically solving for the Q of the solution. Okay? So, when you read this question, you have 50 milliliters of this and 50 milliliters of this. When you combine them together, that's your solution. So the volume of the solution is 100 milliliters. This mass, however, needs to be in terms of grams. So we can use our density, which is 1 gram per milliliter. So we would multiply this by the density. And that's going to give you the grams of the solution. So we now have the grams of the solution. We're given the specific heat capacity, and we know the delta T. The specific heat capacity is in terms of Celsius, so you don't need to convert the temperature. So let's solve this out. We have Q of solution is equal to 100 grams of solution times 4.184 times, when you subtract the two temperatures, you get 0.81. That's going to give you a solution of 338.9 joules. The question is specifically asking for the delta H of the reaction. To solve for delta H of reaction, we need the Q of reaction. And we know Q of reaction is equal but opposite to Q of solution. So our Q of reaction will be negative 338.9 joules. And it's per mole of our solid substance in the reaction. So our AgNO3 is the solid substance. We need to figure out how many moles of AgNO3 are present in this original sample. We know that the molarity is moles per liter, and we also are given the volume, so we can isolate the number of moles. So we can do 0.5 liters, so I'm switching the 50 to liters, times 0.1 mole of AgNO3 per 1 liter. So we have the moles of our solute, the heat released from our solute reacting in solution, and now we can figure out our delta H of reaction, which is going to be negative 338.9 joules divided by 0.005 moles, giving you negative 67. This is probably the absolute worst type of calorimetry problem you can get. Okay? So, again, I wanted to show you the crappiest, so then when you get to the exam, you'll be able to do the easier ones. Okay? I'm going to do another one that's a little bit easier, but I wanted to show you that one. Again, I don't think that they expect you to be able to do something like this in a minute and a half. But if you understand the concept behind it, then you'll be okay for the exam. You definitely need to know how to do coffee cup calorimetry though. So make sure you read that section in your textbook. All right, I'm flipping the page. And I'm going to do the first one. This is another calorimetry problem. Oh. Okay. So we're going to do the same type of process. We know delta H of reaction is Q of reaction over moles of our solute, which is zinc. Because we're adding zinc to a solution of hydrochloric acid, okay? We know Q of reaction is negative Q of solution. And we know that Q of solution is MCAT. Okay? So, again, they give you the density, and they give you the specific heat. So what we need to do is we have it says make a 50 milliliter solution. So that's the volume of our solution. But we need the mass of our solution. So to get our mass of solution, we need to multiply the volume by its density. So we have 50 milliliters times 1 gram per milliliter is going to be 50 grams of solution. That's our M. Our C is given, and it's in Celsius, and then our delta T is given. So we say Q of solution is 50 grams times 4.184, which is given. And then our delta T, if you subtract final minus initial, is 1.2. This gives you 250.8 joules. This is Q of solution. But to solve for delta H of reaction, we need the Q of reaction, which is equal and opposite. So Q of reaction is negative 250.8 joules. The next thing we need to solve delta H is the moles of zinc. So we were given the mass of zinc in the solution. So we just convert it into moles. So we have 0.013 grams of zinc times 1 mole over 65.38, which gives you 0. Okay. We have the two components now, so now you can just plug it in and get your answer. I'm sorry? Not necessarily. That's supposed to be negative. Yeah. Thank you. So this answer is negative. A lot of times the answer will be in kilojoules, so just convert this over to kilojoules. So you'd get 158.7 kilojoules. Okay? Does anyone have questions? Yeah, it's in, oh, yeah, negative. Thank you. Okay, so take a breath. We're done with calorimetry. Please review that still if you're still having issues. Okay, let's move on. So this one, now you're talking about the different trends. So it says which pair is the first larger than the second? And you have a bunch of cations and neutral and anions. What's the trend? Which one are the largest? The cations, the neutral, or the anions? Okay, so the anions are the biggest and the cations are the smallest. So cations are small, anions are big. Anions have more electrons, so their outer shells get larger. So if it says which one is the first member larger, we're looking for the first one to be less positive than the second. The first one right here, that's more positive. These are the same charge. Here, we have a +1 and a +2. As we get more positive, we get smaller. So D will be your answer. Because cations, the more positive you are, the smaller you are. Yep. You're good? All right. So flip the page. We have another trend. We have the ionization energy. So remember, ionization energy is the energy required to remove an ion, okay? When you're doing a problem like this, you need to say, where is the jump in energy? So here from 1 to 2, we multiply by 2. It pretty much doubles. But then when we compare 2 to 3, it multiplies by 4. I can't tell you by which factor is going to be like too big of an energy gap, but when you're comparing your question, just look where the largest gap of energy occurs. And what that means is you don't want to go any farther than the second ionization energy because it requires way too much unfavorable energy to do that. So in the first step, we remove one ion, so it's a +1. In the second step, we remove a second electron, so it's a +2. Then it says, no way, I am not going to a +3. So your answer that's most stable will be a +2 charge. Yes?
Okay, so the E1, like, the E1, what is required to take one ion off, or it's like the jump from E1 to E2?
It's required to take one electron away. So it's going from neutral to +1, and then +1 to +2.
So E1 would just be neutral.
E1 is going from neutral, and then when you add that energy, you go to +1. So it's the energy required to remove that first electron. Okay? Yeah. Well, if it was an anion, it would be electron affinity instead of ionization energy, and they probably won't ask a question set up like that for it. Does that make sense? Okay. All right, so flipping the page. Flip it again. Zoom out so you can see it. I'm on this page with bonding, and then I'm flipping one more time. So it says, what is the electron configuration of the zinc ion? Okay, remember, zinc is one of your transition elements. So when you're forming an ion, the way I recommend doing this is if you're not very good with this, write out the electron configuration of neutral zinc. So right now I'm writing neutral zinc. When we form the zinc 2+ ion, we get rid of 2 electrons. With transition elements, which electrons do we take from first, S or D? Good, you take S before D. So when you form your zinc 2+, you're going to have argon 3D10. If you formed zinc 3+, then you would start taking from the D orbital. Yes?
If there was an ion that included the P's as well, would you take from the P's or from the P's?
Yeah, so if you have like chlorine, so a main group element, you take from P before S. Yep, good question. Any questions? All right. Whew, we're almost there. I'm tired. Are you guys tired? 30 more minutes. Did you guys eat lunch before you came? Oh my gosh, that was your first mistake. Me either, but that's okay. Hopefully you guys woke up late, so you ate breakfast late. Okay, so the next question is asking which of the following is isoelectronic? So isoelectronic means the same number of electrons. So it's different elements that have the same number of electrons. Hint, hint, you should have different elements, one, and you should have ions. Because if they're the same element, they're not different. Never mind, ignore it. All right, so what you would do is add up how many electrons are in each of these. So for time's sake, I'm just going to add up the one of the answer. So chlorine, we look, chlorine neutral has 17. When you form a -1 charge, you add 1, so that gives you 18. If we do sulfur 2-, sulfur has 16 normally, but then when we form the 2-, we add 2, which gives you 18. So when you went through and did that for all of them, this is the only answer where their number of electrons will be the same. If you notice, your answer will always they'll fall on the same noble gas. So if you follow the trend for the periodic table, they'll always end on the same noble gas because that means they have the same number of electrons. So that's kind of a shortcut for you guys to do that. Okay, so flip the page. Number 7. It says, which of the following is most likely to be a free radical? Free radicals, I want you to know, have an odd number of electrons. So remember how you did all your Lewis structures and you needed to add up your valence electrons, blah, blah, blah. Yeah, you do that here. So you add up the number of valence electrons in each one of these. If the answer is an odd number, you'll have a free radical. So when you add up D, nitrogen has 5, oxygen has 6, so that gives you 11. Chlorine has 7, and each oxygen has 6, so that gives you 19. Both of those numbers are odd, so that's your free radicals. Does that make sense? You don't need to draw out each and every one of these, just add up their electrons, okay? The key thing is that it's odd number of electrons. Okay. Which of the following compounds has the strongest ionic bond? This is your Coulomb's law. So we have the force is QQ over R. You guys remember that from the exam? Okay. So Q is your charge magnitude and R is your distance. The stronger the greater the F, the stronger your bond. So you want F to be as large as possible for a strong ionic bond. That means you want your charges to be really large and your radius to be really small. So Q and R small. So the first thing we need to do is compare. I always compare charges first and then use sizes if you have issues. So Mg is a +2, oxygen is a -2. So just kind of multiply those two together. So you get 2 times 2, which is 4. And then we're going to do that for the other ones. Potassium is a +1, bromine is a -1. So 1 times 1 is 1. And you're going to do that for the rest of these. These values are coming from their charges based on the periodic table. Bless you. Okay. So these are the magnitudes of the charges. Once we get to this point, we can automatically cancel these two out because their charge magnitude is much smaller than the other 3. The next thing we need to consider is our R. So we need to use our radius trend on the periodic table. Which way does the radius trend work? Up and to the right or down and to the left? Good, down and to the left. So for R, we want R to be tiny. So we want them to be as far up and to the right as possible. When you compare the 3 of these, MgO is the smallest. Okay? Compare their cations first, then their anions. It doesn't matter how you do it. Just pick one, compare them, and then compare the other. But you'll see that the magnesium and the oxygen are always the 2 smallest ions of all your options. So again, for the strongest bond, you want the greatest charge and the smallest distance. Test? Do you guys remember what test this was, 2 or 3? I think it was test 2. It's under the section of Coulomb's law, but I can't remember exactly which test.
I think it was test 2.
Test 2?
Test 3.
Okay, I think it was test 2. Okay, thank you. All right, so let's do a little bit of Lewis structures. Hey, these are fun. Okay, so this question is asking which of the following are valid Lewis structures. So remember, you always need to check for your octets being satisfied and that you have the right number of valence electrons. So let's go through. All 3 of these, just to let you guys know, are C2OH6. That's their formula for all 3 of them. They're just arranged differently. Excuse me. And they have 34 valence electrons. When we look at the first one, do you see something wrong? Yeah, hydrogen can only ever form one bond, so this automatically is wrong. This compound right here, you may have never seen something like this, but are all of the octets satisfied? Yes. Also, if you want to triple check, you can add up the valence electrons and it will add to 34. So this guy is good because he has an octet around each one of his atoms. When we look at this, are all the octets satisfied? Yes, and they will also add up to 34 valence electrons. So both of these are valid Lewis structures. Again, they may not look familiar to you, but if you check those two rules and they both work, you're fine. Yes? Am I wrong in adding? 36, right? Is it 36? Oh, yeah, I just can't add. Yeah, so this is 8, 6, and 6 total. Right? Yeah, 20. Wow. I don't know where 14 came from. Oh my gosh, that's really bad. Yeah, 20 valence electrons. So if they add up to 34, then you're really wrong. Sorry about that. I did this during dinner last night, so my food was probably more important. Yeah, 20 valence electrons. Thank you for that. So add correctly first. Any questions on this, though? Okay. That took you guys way too long to call me out. You need to call me out quicker. No, yeah. If you see a discrepancy, tell me, because it's probably my fault. All right, so I'm flipping the page. Whew. Alrighty. Okay. In which of the following compounds can a valid Lewis structure be drawn, but it's permissible to violate octet rule? So remember, row 3 and down can have more than an octet. But you need to draw out each one of these compounds to figure out which one actually violates it. So when you draw all of these, yeah. Yeah, you can shortcut it. These are the only two that potentially can, right? Okay. Oh, it can too? Okay. Sorry, I don't have a periodic table with me. Okay, that's where this, hold on. I'll explain to you what this question is asking. Okay. So, it's saying, which of the following actual structures can violate the octet rule? There may be multiple structures that have the potential to violate the octet rule, but it depends on the actual structure you're drawing. So if you look here, the only one that needs to violate the octet is this one right here. I know other ones are possible to violate, but because of the formula it's in, there's no reason to. So, this is the answer right here, because it's the only one in this structure that needs to violate the octet. Does that make sense?
Which elements are allowed to violate it?
So row 3, the horizontal row 3 and below, they're allowed to violate or have an expanded octet. Good question. Okay. What is the formal charge on the nitrogen in the nitrate ion? So remember, formal charge is going to be group number minus the number of dots plus lines surrounding that particular atom. So when we draw nitrate out, we're going to get this structure. We're specifically looking for the nitrogen. So nitrogen is in group 5. And then we're going to subtract the number of dots plus lines. Nitrogen has no dots, but it has 4 lines. So it's 0 plus 4. And that's going to give it a +1 formal charge. Does that make sense? What would the formal charge of this oxygen be? 0. And this oxygen? -1. When you sum the formal charges together, it needs to be equal to the charge of the compound. I know you cannot see that at all, but it's NO3 minus. Okay? I know it does not really show up at all on your paper. Okay. So, in the resonance hybrid, which of the following is observed? And this part of the answer is on the back. Sorry, the printer decided to like have a freak out moment. Okay, so resonance hybrid, remember, okay, you have resonance structures. For this compound, your resonance structures would be having the double bond on any of these 3 oxygens. Your resonance hybrid, however, is the sum of all 3 of those hybrids together. That's like the true structure. So resonance hybrid is the true structure. What that means is it has a partial double bond around each one of these oxygens. Because there's 3 potential areas, you would say there's a partial double bond, you'd say a 1/3 chance at each spot. So when you flip the page and read the rest of the answers, we see all of the bonds have a bond, thank you. All of the bonds have a bond order of 1.33. The bond order tells you what type of bond is present. And in a resonance hybrid, because there were 3 areas that you can have a double bond, you have a single and a third part of, like 1/3 of the double bond. Okay? Does that make sense? Okay. In a resonance hybrid, this little part of the double bond can be on any of the 3 oxygens. The resonance hybrid is like this when you squash all 3 of them together. So you would say this double bond is like 1/3 on each one of the oxygens. So all of them have a single bond, and then they also have a third of the double bond. So when you read this answer choice, it says all of the bonds have a bond order. This indicates bond type. So whether it's single, double, triple, partial, of 1.33. So it's saying you have 1 1/3 bond, basically. That's because it's asking for resonance hybrid. If it's asking for resonance structure, you would say you have 2 single bonds and a double bond, because that's just one of the isolated structures. So because it's the hybrid, C is the right answer. If it was just asking for one of the resonance structures, D would be the right answer. Does that make sense? Okay. You guys can review like naming and stuff on your own. I think you guys are capable of that. Okay. Let's do a little bit of hybridization. Bye, thank you for coming. Okay, so we have ethylene right here, and it's asking what the CC pi bond overlap is. So ethylene has a double bond. What is the hybridization of this carbon? sp2. Each one of these carbons are sp2 hybrid orbitals. Remember, 1 + 2 is 3. There's 3 bonds around it. Okay? There's 3 potential bond overlaps that they can ask for. They can ask for the CC sigma, the CC pi, or the CH sigma. In a single bond, what is your sigma pi distribution? A single bond is 1 sigma. What is a double bond? A 1 sigma, 1 pi. And a triple bond? 2 pi, 1 sigma. Good. So in this thing, in this double bond, we have one of the sigmas and one of the pi's. The sigma bond is always the hybrid overlap if you have that option. The pi bond is always the p orbitals. So if it's asking for the CC pi bond, what would your overlap be? C CP to CP. That's the pi bond. The sigma bond would be CSP2 to a CSP2. And the CH sigma bond would be CSP2 to an H1S. 1S because you don't hybridize hydrogen, and hydrogen is in the 1s, like its unpaired electron is in the 1s area. So your answer is B, because it's asking for the pi bond. What's the hybridization of this oxygen? Good, sp2. If we have, I know I accidentally switched it between Br and F, it doesn't really matter, this is Br. If we have HBr, what's the orbital from H? 1s. And what about Br? For P. Because bromine is in the 4th N level, and it's in the P subshell. You don't need to hybridize either of these because they both have an unpaired electron to form the one bond necessary. So your bond overlap would be a 1s to a 4p. You did not need to hybridize these. Okay. Gases. This is our wonderful PV equals nRT. Okay. So how many ozone molecules are in 1 liter? When you guys do the gas law equations, I always recommend writing out what's given, because then you can figure out which equation you need to use. So they give you the pressure. They give you the temperature. The volume is 1 liter. We don't know N. And R is always 0.08206. That's a constant. That should be given on the exam. Yes? Yeah, because the constant is in Kelvin. Yeah, always make the temperature Kelvin. So if we need the ozone molecules, we need to get the moles first. So we have N is equal to PV over RT. And that gives you an N value. Of that many moles. Once we have the number of moles, how are we going to figure out how many molecules we have? Yeah, Avogadro's number. And And that's going to be how you figure out how many molecules. Again, this is kind of complex, but I think that it's a fair game question because it doesn't take you too much time to solve out. Does anyone have questions on that? Okay. So if you flip the page, I'm going to do a couple more problems before we finish out here. So remember how we have STP, standard temperature and pressure? It's saying at STP what volume of N2 reacts to produce blah, blah, blah. So we're trying to figure out N2, but we start with the volume of H2. When you're at STP, it is okay for you to use the mole-to-mole ratio. You don't need to do PV equals nRT and do a bunch of stuff. You can just compare the mole-to-mole ratio of hydrogen to nitrogen. This is only when you're at STP. So we can say 22.2 liters of H2 times our mole-to-mole ratio. So we're looking for a volume of N2. So we have 1 mole of N2 to 3 moles of H2, and that gives you 7.4 liters. If you want to use PV equals nRT, you can, but this is the shortcut. So at STP, you can use the mole-to-mole ratio to compare the volumes. The next question is it's saying, place the following in order of increasing velocity. So when you are increasing your velocity, are you bigger or smaller? Good, smaller, move faster. So pick the one that goes from heaviest to lightest, which is E. Yeah.
What is a mole?
A mole?
Yeah.
It's an animal. No, I don't, it's just it's like a unit of measurement. So like length, yeah. No, yeah, it's just a mole. So on my graduation cap, I'm gonna have a dancing avocado singing Avogadro's number. Is that super nerdy or what? Yeah. Okay, let's do this last guy right here. So which gas has the greatest volume at STP? So we're going to look at our PV equals nRT. We have V is nRT over P. So it gives it to you in grams, but our PV equals nRT compares moles. To have the greatest volume, you want the greatest number of moles. To go from grams to moles, you're going to multiply number of grams times 1 mole over number of grams from the periodic table. So if we want the number of moles to be as large as possible, decreased molar. There's a short semester. My phone number, email, I'm more than molar mass.
You worked on today.